So we're going to start with a quick overview of for loops. I feel like we've gone over this before, but I'm just going to redo it one more time. You guys remember the function, how you write a function? So it's function, here's the return, name of the function, and here's the parameters. Okay. So what we're doing is just summing all integers from 1 through whatever integer we're inputting, basically. So if I type in add in 10, you're going to get 55, because that adds up every single number up to 10. Yep. So the general format for loop is you say for, this is some variable, equals, and this right here is a vector. I feel like we did cover for loops, because I told you about how this makes a vector, but when you print it, it just prints out each value of the vector. So what I could do is I can go who's, actually this won't work, sorry. If I did who's on this workspace, because remember I told you this workspace is separate, if I did it on this workspace, you'll see that I is not a vector. I is actually just an int. But this is a vector, so it loops through each element of the vector. Okay, so it'll start with 1, then go to 2, then go to 3, then go to 4. And this just adds it up. If you wanted to add every other one, you'd do like that, and that would skip every 2. The middle one's your increment. So it goes start, increment, end. So I redid this. 25, because it skips every other one. Got it? And if I did 9, I think, you get 11, because it would do 1 and 10. Good? Okay. So that's our quick little refresher on loops. So I think what we'll do, let's see if I find it, is we're going to go over, do you see it? Oh, it's right here. There you go. The trapezoid method. Okay. So, some decent chalk. Is there any big chalk in here? So where we're going right here. The given function that I have is that f of x equals x squared plus 2x plus 1. That's the function that we're doing. And you know that it's going to form a graph variable, right? I'm showing you on our variable. You know that if you want to find the area, you guys know how to integrate, right? So if we integrate from a bounds of a to b, you can do the actual integration where if the Riemann sums, you add up the Riemann sums, and the type gives 2. Trapezoidal method splits it up. So it takes from here to here. It forms a mini little trapezoid. So it takes this length here, and it does this little, so trapezoid looks like this. That's one of them. And the second one here, let's do this one. Not much of a trapezoid. This one here. Like that. Yep. And as you close this interval up, it'll get more and more precise. Kind of like Riemann sums, but trapezoids. So this is a method to integrate that's super helpful. So the first thing we're going to do is we're going to write our function, which is x squared plus 2x plus 1, in this, you can name this whatever. I'm naming it a given function, or given func. But we have a function f, which is just given function of x. It's only of one variable right now. It's of only x. Okay? So we can do this f. You can also do systems of equations. I'll show you that later. But if you want to just input one equation, you do f equals x squared plus 2x plus 1. So this isn't actually an equation. Like, it's not actually storing that. You have to put in an x, and then it'll give you the value. That's what it does. Matlab can't really store equations like you and I do it. But what it says is that if you plug in like x equals 0, it'll go 0, 0, f equals 1, and it'll return 1. So in that way, it's actually a function. Do you see that? If you put in an input, you get an output. You can't change what happens in between, but it's that function that happens in between. Are you getting that? Okay. So we have this thing. Now we go to our trapezoid method code. So function return equals trapezoid of a, b, n. Okay? So we have three things, A, B, and F. So here's A, here's B. A's your starting, B's your ending. N is the number of intervals you want to have. So n is how many, so if you had n equals 1, you split it up once. N equals 2, you split it like that. 3, you split it like this. 4, you split it like this, so on and so forth. Do you see that? Okay. And obviously as n gets more and more, as n gets larger, you get more and more precise. Yeah? So we're saying that this return equals 0, and we have this dx. What dx is you come over here, you take this final value, you take this initial value, and you divide it by this n. So if b equals 10, a equals 0, n equals 10, dx is going to be 1. That means that your step size is going to be 1. So when you integrate, like I said before, this step size is going to be 1 large. If n equals 20, it's just going to be 0.5. If it's 100, it would be 0.1. You get that? And the way the trapezoid method works, the error is actually an order of x squared, delta x squared. So if I go from 10 to 1, that's a pretty big jump. But where it really works is you want to have your dx's less than 1. Because if your dx is, let's say, 0.5, and you go to 0.4, 0.5 squared and 0.4 squared have a bigger difference. Does that make sense? I mean, I know it does get smaller, but it's of the order. So it's like, basically, this gets exponentially smaller, is what I'm trying to say. So you really want to try to minimize that dx. But that then takes up more computing time. That's kind of the trade-off. So what we're saying is area equals this plus this over 2 times dx. So what I'm saying here is, this again. Do y'all want to scoot over there?
I would just like to do.
Alright, fair enough. I'm just want to keep walking in front of the screen for y'all. There we go. Equals f x plus dx. That's not integrate, that's just the dx variable. I should really think that delta x. This is your equation for area. Okay? So write that plot. Take this guy and this guy. So some value here, some value here. You average that value and you multiply by that dx. That's kind of how that trapezoid method works. So smaller the dx, of course, is closer that averages to the endpoints. The problem with this is if you have a big dx, like this on a sine function, and your dx goes from here to here, your area is going to come out as 0. Which is right in this case, but there's cases where this won't be right. Does that make sense? Like, let's say it's a really, really small dx, and it goes like that, and then it comes out like this, and you try to find the area from here to here, but there's actually a little bump. It'll give you that area. The area of the entire thing is 0. So you just have to be careful. You don't want to like lose any areas. That makes sense. And that solves itself if you make dx really small. It's when you have dx equals really large, so you start losing some bumps and stuff. So that's kind of the formula. And do you guys get how that formula works? It's basically the midpoint times the delta x. Yeah, so you're just finding the average and you multiply by delta x. Really simple. And so what we're doing is going from a, going up by dx, to b minus dx. Right? So you start at start at a, you go up by a plus dx, and find the area of this guy first. That's the first loop. Okay. Second loop, you go here. That's a plus 2 dx, right? Because the increment's dx. So you go to a plus 2 dx. Find the area of this guy. So on and so forth. Where are you going to stop? Are you going to stop at b? You want to stop so that the last edge is at B, right? The last trapezoid that you're going to draw is going to go like this, and this is going to be, yeah? What's this going to be? B minus dx. Or a plus dx times n minus dx. That's kind of complicated. Don't worry about that formula. Basically what we're saying is you can stop at b minus dx, because what we're saying is this formula goes from x to x plus dx. If you want this value to be b, you need to stop at b minus dx. That's why you stop here, is so that that last edge hits at b. Otherwise, you'd actually go one more over. Everyone see how that works? Okay. So that's why we go from a, our interval is dx, and we go to b minus dx.
You get a negative area if you went to B, right? Because it would be below the curve.
Yes, for this graph, yeah, it would be. If you said b at, well, I mean, we said b at this intersection, right? If you said b up here, it would still be positive.
Right, I just mean in this case. It would
Yeah, in this case, it would be negative. Yes. Do you see why that happens? Everyone clear on that? Okay, perfect. So that's your area function, and the return, I'm just adding them up. Okay, so let's play around with this. Let's say trapezoid of 1, 10, 1. It's giving me 562 with a n of 1. Now if I make that 1 a lot bigger, you see how that drops a lot? Oh, shoot. What that's telling me is that when you have 1, it's actually overshooting it, right? So then what do you think that graph looks like? It's a little more abstract. Yeah, there you go. So this graph that I drew is actually incorrect. What it looks like is like that. Yeah, I mean that's what you know that from the equation, right? But if you didn't know the equation, this is the way to tell. Is you put 1, it's going from 1 to 10, and it's forming this huge trapezoid like this. And that has an extra area here. That's what's happening. Then when you split it up to a million, it's getting a ton of little ones, and it's getting closer. But it's still approximating over. Because your concavity is greater. If you take this point and this point, your line is always going to go over. Your concavity is down. You take this point and this point, your line is this point. Your line is always going to go under.
I don't know if this is pertinent right now, but is there a way to output your tabulation time? So, for example,
Yes.
you could optimize numbers.
Yes, I was going to show you that right now. It's called tick and tock. It's this funny little function. Tick here, tock here. That's it. So now, let's do the 1. Elapsed time is that many seconds. And then I do 10,000. And there's your difference. Yeah. So tick and tock is really useful. You can put multiple tick tocks if you want. So I could have put one inside the loop. That displays every time it loops, it'll run it for you. That's not useful here because if it's running 10,000 times and each one takes, half a millisecond, it's going to give you millions of 10,000 different outputs.
Can you output that as a parameter or a variable?
What would
you wanted to,
add them up or something?
no, like if you wanted to plot accuracy versus computation time.
You could, yeah. There's a way to do that. We could do that right after if you want.
Yeah.
Yeah, I can write that code for you.
Just curious.
Yeah. Talk is also a variable. Tick is not a variable, talk is a variable. Which is, I don't know why that works like that. But tick is not a variable, talk is a variable. But yeah, let me finish this little demo and then I'll keep going. Add a few more zeros. Now it's taking some time. This might actually crash it. This might be too many. Anyways, that's significantly more zeros. Yeah. And each zero here means a lot more for Matlab than these guys over here. Go ahead and terminate and drop some of these. There we go. Okay. So you don't want to go that many zeros. That's poor computer can't handle it. But do you see how it converges to 441? Now if I went back to like 10,
you can kind of see how going from 1 to going to 10 has a huge increase. You went from 563 essentially to 442. You're only off by 1 here. You were off by over 100 before. Do you see how a little change in n, the change in dx is a huge, huge factor. That's why I said it's that n squared. But then if you go from 10 to 100, it's not that big of a difference. And if you go to 1,000, it's not that big. It's basically converges. Does that make sense? Because it's that order n squared. So it all depends on how much accuracy you want. I'd say never run under 1,000, 10,000.
I usually use 10,000.
10,000 is my usual standard. But it also depends on your function. If once we get into different, like solving differential equations and stuff, you might not want to run 10,000 times because that might crash your computer too. Okay. All right. So you asked about running different computation or running different amounts, and then also like plotting time versus that.
So I was just gonna try to do this. Can you plot, do an array of n and then plot n versus output time?
Yeah. So we could write that on here actually. So instead of doing this inputting n, we get rid of that. We can leave dx here. We'll say for j equals, and let's go 1, 10. Where's the... I don't want this inside the loop, do I? Yeah, I want this inside the loop. Okay. So J's going to go through all those values, right? So we could say like that. That's valid, right?
You want the table side as well?
I think so, because what I was going to do is I was going to say, I was going to create a value of, say, times. We could just say times equals 0, like that. And then we could,
So times at j equals time.
yeah, I think you could do that.
I think you can.
Times at j, and then I need it inside that j thing, which is okay, still inside that. So we do times at j, or I have to do like that, and then I'd have to create a count. Count equals 1. Remember, it starts at actually. Make that 0. Or,
No.
yeah, 1. Yeah, you're right. You know what? I don't know if we can do that because J's that variable of the loop. That's not going to let you do it. Let's just do times. Let's try this. What is it printing out? Is that right?
Yeah, that's right.
There you go. Yeah. Only thing that for your plotting, I put this j inside this loop. This won't let me access this j because that j goes through. So you have to just recreate this array and then plot it against that. And I mean, it prints out that ret because that's my return. That's it. What would you want? You want vector on this times. There we go. Good.
So this isn't great because those are your points. But you see how they get exponentially larger? Yeah. This is an exponential line. It's just not fitting well.
Good. Okay, that was good. That was a good little segue there. If you have questions like that, feel free to speak up because I was. Yeah.
Can you make it like logarithmic accident?
Yeah, you can do log plot.
Semi-log.
No, what's the? Is that how you do semi-log x? And I mean, you can just search up here. There you go. Well, it's closer. If you had, 1,000 of these, it'd probably work a little better. Because
You kind of see it. And I mean, this is also variable because my computers, when you do, there's other stuff that goes on behind the scenes that on an ideal computer, this would be exponential here, or it'd be logarithmic there. What's actually going on is once it starts getting here-ish, Matlab itself doesn't actually allocate more data to itself, more memory to itself. Once it gets up here, it starts allocating more data to itself. Because it realizes it's running a large program, it'll actually start stealing more memory. If you could limit that somehow, then this would come out perfectly well. But since it's not, that's why this area looks a little faster than it should be. You'd expect something more, linear, right? But you're not getting a linear line here because, especially in this region, it's starting to allocate. But here, it's just such a large number. No matter how much memory you allocate, that's all that Matlab gets. Like that's just based on I have an 8 gig processor, 64-bit machine. That's how long it takes.
And then that gets into like there's stuff that you don't want to, computer science stuff. Okay.
So
Sound?
that plot should be linear.
Because the original plot
Plotted
should be,
against the log.
yes. I think you just sound like y might work, it should work better. A little better, but yeah. You know what might be better is,
Maybe it's log.
no, I think I'm gonna try, no, actually it's fine. But yeah, you can play around with that yourself. But if you change those numbers from starting with a big number and going higher and going like smaller increments, that probably work out better for showing you the real shape of it. Okay, so that's the trapezoidal method. Do you guys have any questions about that? Everyone good? Everyone get what's going on with the trapezoidal method? Okay, perfect. Then I think we can move on to our next method. I have TikToks on here. Okay. So this is the Simpson method.
This is another way to integrate functions. Do that same function. Right? That's right. Alright. So where area equals this dx over 3. Then we're going to do
Yeah, that's right. So that's just I plus 2 times dx at the very end. Okay? So,
what this does, similar to the trapezoid method, but it's a little more accurate. In theory, it should converge a little faster. Because, same graph again, I'll take this point, which is my, at I, let's say. Let's say dx plus 1, dx plus 2. It takes those points, and it takes this value plus 4 times this value plus this value. And then it divides that by 3. So in trapezoid, you're doing that, right? So you undershoot it by more. Here you're creating this trapezoid 4 times this guy, and then this trapezoid. So what you're doing is you're weighting this middle guy a way, way, way more. Does that make sense? This middle guy gets weighted way more because that's closer to the midpoint. Or that is the midpoint of your dx. If you have a dx, if you have I plus dx, I plus 2dx, the I plus dx is your midpoint. So you weight that a ton more, and then you divide it by 3. And that evens it out. That averages it out. You see? Okay.
So I can show you an example really quick. I don't have that. I have that trapezoid method. I wrote it to my method, so I don't want to change it back right now. But do you guys remember the values were like 441-ish? I think that's what it converged to. Correct me if I'm wrong. So it's kind of converging. But do you see at 10, it's already a bigger error than that thing was at 1? It seems more inefficient, doesn't it? I mean, also, it's more precise, but it's also more inefficient. And that's the trade-off you get. Because, you're calling the function more times. But that's just proof that it converges. Now let me go over the intricacies of the code. Let's go from here. There we go.
So, TikTok, same thing. Return equals 0, area equals 0. dx is the same code as before, where I split this interval up into n subintervals, then my dx is going to be this large, delta x. And then I have this d step here. This is purely for the loop. D step is not used in the calculation in any way. D step is purely here just for dx times 2. Because my loop is going to start at a, go up by b, and it's actually going to go up by dx times 2. Right? Because I start here. My next one is not this, it's actually this. Right? So I start here, go up by 2, go up by 2, go up by 2. That right? And it ends at b. Are we good? So it starts at a, goes up by 2, ends at b. Now, why isn't it b minus d step? Can someone tell me that? Remember the last one was b minus dx? Was where we stopped it? It's a little tricky.
So do we agree that it converges to the same value? So this is the right value. Now what if I did b minus d step? Because you assume that, right? Right. But this is...
I think there should be a D step.
Oh, wait, I should flip that. My bad.
I meant to put this up first and then show you why it wasn't. This is correct. My bad. I meant to show you the other way around and be like, oh, why? This is correct. You stop at d step minus that. Same logic as before. But I meant to show that incorrectly and then.
Alright, that's my bad. But also, do you see how this barely affects it with a d step of this? What was this value? 0.002. You see that? Because that d step error is very, 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 very small. So it doesn't actually matter how you write this code if your d step's small enough. Which I know is a terrible thing to tell you people, but you can get away with a lot of things in numerical methods because your code's like, if you make that interval small enough, it kind of doesn't matter. Okay? But this is the correct code. My bad. Okay? Everyone good? Alright. And then do you guys get the rest of this code? I just copied that formula put over there. Where it's function I plus dx, I plus 2 times dx.
So with all these numerical methods, you're basically doing like a trade-off between the number of iterations that you have to do, which is like the speed at which it converges, as well as the number of functions that you need to call. So in Simpson's method, you're calling given func 3 times. But since given func is just like a simple quadratic, it's not that big a deal. But later on, when you're doing like real applications, a given function will be a huge function. Maybe it will be a function of different functions. And in that case, you want to minimize the number of function calls that you make. And you might want to use trapezoidal rule, but that will make it convert slowly. So in reality, what you do is you just try a bunch of these methods, and you use a bunch of time steps, and you see which one is the most effective, and then you carry that on forward for the rest of the application. It's a little bit of an art on that side.
It's way more of an art. Numerical methods is kind of really hazy, but I mean, this is kind of what you're going to get into is like a lot of hazy stuff. Do we get this? Is it good if I move on? Okay. So that was 2 things we did to integrate. Yeah? Let me see if I can find Newton Raphson anywhere. Okay.
Bisection.
No, I'm going to do successive. I'm going to do solving of iterative solving now. That good? I don't know where my Newton Raphson code went.
Usually start with bisection.
I'm going to start with successive because then we can go straight to bisection.
No, that's successful. Go ahead.
I don't see my Newton Raphson though, so I'll have to write that at some point. Okay. All right. So
This is successive is a really you'll use the other methods more. This is for really simple things where you could almost argue that you don't need this, but who knows? X equals cosine x. That's your function. What's the value of x? You don't know because it's not easy to solve, right? So what you can do is you can guess the value of x, and after you guess the value of x, you plug it in here, and you get an answer of x. Take that value, plug it back in, get a value of x, plug it back in, get a value of x, and keep plugging it in until those 2 values match up. That's what successive is. Successive substitution. This side can be as complex as it wants, this side can be as complex as it wants. You just basically need to have x equal x. And it needs to be so you can't eliminate it. So if this was x squared, this was x, you could solve that. You can't solve this. We good? Okay. So, we go through this code. Clear everything. Here's a tolerance.
Can you solve x squared?
X squared. If x equals x squared, you can solve that.
Oh, I thought you said x squared cosine x.
No. If it's x squared cosine x, you can still solve it. But I'm just saying if you have something like x equals x squared,
Okay.
bring it over and factor it out. Same way you know. So what we're going to do is define this tolerance. This variable is going to show up a ton from now. A tolerance is basically how small or how large you want to let the error get. I said 10 to the negative 5. If I said 50, I'm okay with the error being 50 large. I haven't told you what the error is yet, but I'm okay with it being 50 large. I'm not okay with that in reality. I want something small. 10 to the negative 5, I'm not looking for huge decimal places. If in your research or if in your work you want something down to like 50th decimal point, get a new, don't use Matlab, but also make this really, really, really small. And you'll probably be doing it on supercomputers. But usually like negative 5, negative 7, what do you usually use?
Negative 5.
Negative 5 is my usual standard. Because I mean, I'm looking for mostly the what's on this side of the decimal place plus, a little bit just to know what's going on up there, basically. And this error equals 1. Make sure when you initialize it, it's greater than this tolerance or it's not going to run. Don't forget that. Don't make this error smaller or you're not going to run. And then your first guess. I'm just saying x of 1 is equal to 1. I have no idea what it is. It doesn't matter. The closer you are, the less iterations it takes. But whatever. We have a computer. And then I equals 1, just an index. So we're saying, while this error is greater than this tolerance, x at I plus 1 equals cosine of x at I. So, initially, set it all together for you guys. plug in 1. What's cosine of 1? Don't worry. Let's just say pi. Cosine of pi is not 0.
Negative 1.
Negative 1. What's your measure?
Oh, I got that. Not math.
Negative 1 you plug in and then it's some value here. Plug that here and it comes out here. You know, and then the moment these two match up, you're good. If you did sine x equals cosine x, sure, I get, that's tangent. You can solve that. But if you really want to be clever, you can do sine x equals cosine x, solve it, and it'll catch at pi over 2. Or pi over 4. Because at pi over 4, they both equal. So that's how this kind of works.
Is there a chance this method can like diverge?
Yes, it can. I'm going to get that later. This will diverge a ton. Most of these will.
I'm telling you, numericals more, like he said, it's more of an art than a science. Your initial guesses, if you, so for my research, I had this one code where if you started it at like this value of 3.5, it would converge. 3.4 would diverge. It's stuff like that. Like you just don't know what to do with it. You just guess and hope for the best. So we're saying the next guess of x is equal to cosine of the previous value.
You also want to try to make it so it's just x here. So if this was x squared, you do square root of cosine x. Because you want to make this as close to x as possible. Otherwise, this side gets weird. Because you see, if this side's x, I can just get that value and plug it in for the next value. Otherwise, I have to go through some other calculation on this side to actually find what the actual value of x is that I can put for I plus 1, and then run that back in here. So I guess what you could do is you can make this, if this was x squared, you could leave it, get this value, make this some a of something, and then say x of I plus 1 equals the square root of a. You with me on that? Yeah, so you basically just, you want to get this pure value of x in here, and you're going to make that the next one. Then we're defining this error function. Make sure you update the error function inside of this while loop or it'll run forever. Error equals the absolute value of this cosine value minus this x value. So cosine of x at I minus x at I. So I'm finding the absolute value of the difference between this value and that value. So this entire side after you plug in x minus this value. So right now it's going to be pi minus negative 1, so it's going to be pi plus 1, which is a large error, right? That's bigger than this tolerance of 10 to the negative 5. So it's going to run again. It'll keep running again and again and again until it gets to something where this difference between this value and this value is less than 10 to the negative 5. And that's when it breaks out. Are you with me on that? Does that make sense to everybody? Right. So this will just basically, it's like you're just shooting in the dark. You're just guessing numbers over and over and over until one of them sticks. And one of them is close enough, and then you're going to say, okay, that's it. That's kind of what all of numerical methods is. Okay? I have to go in here. Okay. So plug in 1, and it gives you the cosine of 1, which is that. Then it does cosine of that and gives you that. Cosine of that gives you that. Goes all the way through. And it keeps redoing it until it gets here. And then it goes, cosine of this guy is this guy. And then it looks at this and goes, is this minus this similar? Because this is cosine of this guy, and this is this other value. This difference here is less than 10 to the negative 10 to the negative 5, basically. That means that, for my purposes, it's similar enough. The answer is 0.7391. So the answer for x, the root of that function over there, is 0.7391. Right? Because this is also, this is the same thing as writing cosine of x minus x, and I'm basically looking for a root. I'm looking for where that equals to. Right?
The nice thing is, this can get, or this thing is simple. It makes sense to me, at least. I don't know if it's the other methods might make more sense to you or might be easier, but this method to me makes a lot of sense to me. You guess one, get an answer, guess again, get an answer, guess again, get an answer, and just look for a difference. Right. So that's kind of what we're doing here. But this has one drawback in that you need to be able to write it like this. The moment you can't write it like this, it's all bets are off. You can't use this thing again. If I give you some really complex function, you can't do this. If I give you some natural logs with some exponentials and some roots and square, there's just no way you're going to be able to solve that so that you get x equals something. Or if you really want to use this, you could. You could work backwards and like get a left side answer and then work all the way through until you get an answer for x. But in some cases, it's just not possible. Yeah. But this is kind of what it looks like. This method, the successive substitution, does diverge. It does diverge in some cases. Usually, it's good. For simple functions that you're going to be able to solve x for, usually you'll be able to get convergence.
Is it a good idea then to use a while loop?
This is a while loop.
Right, that's why I'm asking. If it diverges, then it just keeps diverging.
Right, so, oh yeah. So you think don't use a while loop.
Yeah, or like, do you have some like exception that's gonna throw?
I don't have on this.
Right.
So you could write an exception. You could create a count. You could say if it hits 10,000 loops, or break out of it. And we have this error function where you go, how do you write error? It's like this. There's an error function. That right here. Write error and then you can basically throw an error. And so you basically say like, if count is greater than, error. Just make this I. There's your built-in catch. So I could write a function that'll diverge. I mean, there's really no point, but that's kind of what we're looking at right now. Does that make sense to everybody? Are you guys kind of getting an idea for what's going on now? Okay. So this is successive substitution. This one's really useful, like I said. Very simple. Makes sense to me. Just be careful with it. That's about it. So I think now we can go into bisection. I think we'll do this one and then we'll call it. Where's the rest of my bisection code? What? It doesn't look like it's... I had it done though. Get rid of it this class. Alright, we might have to skip bisection then. Oh, really quick, let me give you a new... I think we have to skip bisection for today because my code didn't save or something. I wrote it before class, but I guess it didn't save. This I used for my homework. This was a homework problem that I had, and I was able to use successive substitution to solve it. So, take, tolerance, error. Also, use comments. I didn't use comments on this, I'm lazy. Don't do that. Document your work. And I said the first, I'm solving for some kind of velocity. Velocity at 1 is 20.9, is what I said. Just some, I think I had to guess differently, and I wanted to converge again, so I did it closer. I equals 2, and these are all just some parameters that I calculated some way or another. So this nasty thing right here, c times this times log base 10 of this plus this plus this times this, raised to that with that. This is something. It gives you something. Don't worry about what this equation is. Don't worry about that. But do you see how here, everything is C is defined, A is defined, B is defined. This right here is I minus 1. Since I put I minus 1, you have to start at 2, I equals 2. Other times we started I equals 1, we did to the next one. I was just different way of writing it. Something raised to something raised to the negative something. Right. You could solve this with Wolfram. You could plug this in a Wolfram and you could bring that over, set this equal to 0, and ask Wolfram to solve it. Wolfram will solve it a different way. They'll do routes, or they'll do some bisection or secant method or something like that. We'll go over those next class.
but it'll give you an answer. The advantage of doing this is these values are actually calculated on Matlab. I did some calculations here, so using calculator, I used this thing, solved for some values in my workspace, and then I brought it over here. So by bringing it over, I have an exact answer. I don't have to worry about all that typing and making sure everything's right. And this way, I was able to run this code, and I made my error, and I was able to run it, and I got an answer.
So this should converge right now if I tried it. The answer is that. That's some velocity. You don't need to worry about what that means, but that's a velocity that I needed.
Why is it vi minus 1 in your error? Because in the successive one we had now was
I plus 1 minus I?
they'll both have the same I.
Right, okay, so there's multiple ways you can define error. Let me get into this right now, actually.
This will be the last thing I'll call. So your error function, you can choose how you want to define your error as. Okay? So in that case, I was solving for, in the previous case, I had x equals cosine x. And I was solving for where those x's are the same. This case, I have something, 0 basically, equals this long equation. Yeah? But I'm not able to solve this thing regularly. There's no way. There's another v in there. So basically brought it over. It's a pseudo bring it over. And I had a b here. And I said equals something as a function of b. Yeah? I think you can solve this by hand. Like you could manually do this. But it's just a lot of algebra, a lot of calculations. Like I just didn't want to do it. This is quicker. So what I'm doing is I'm saying, if I get a value for b, I want to check its difference from the previous value of b. On the other one, I wanted to check this guy compared to this guy. I wanted to see what this x was compared to this cosine x. I wanted it so that when cosine x equals that 0.7913, x also equals 0.7913. That's what I was looking for. Here I'm looking to see if this next value of b is pretty similar to the previous value of b, because then I know my guess is kind of similar. Here this gives you a solution. Here this kind of confirms my guess. It goes, okay, we're kind of close. It doesn't matter anymore. No matter what I do to this, it's not going to converge. This is a right way to do it. Here you're actually comparing. This is a lazy way to do it, where I'm basically going, is my answer pretty close to the previous answer? Do you see what I'm saying? On the other one, you're actually looking for an answer. You're actually solving for a root. Here, this might be totally wrong. This might be this might not even be a root. This might be like a local minimum. You don't know that. But I physically can say 10.9 meters per second makes sense for this problem. Like flow through a tube, or something like that. I know that 10.9 meters per second makes sense. It has to be within 0 to 50. Basically. This could give you a negative answer. This could never converge. You have no idea. This is the lazy way to do it. Because in the other method, you're actually solving for a root. Here, you're just solving to see the difference. Does that make sense? But this is also quicker, right? Because that one keeps going until that root gets to 0. This one just goes until it kind of converges somewhere, and that just gives you that answer. Then you're going to have to use your brain a little more. Fair enough? Okay. So there's a few ways to define error.
So as I said before, like one of the things you might want to minimize is the number of function calls that you make. So you'll notice this doesn't call any functions when it's evaluating the error. That's a good thing.
That's another thing. I also didn't want to write this again.
Also, you don't need to write.
Or yeah, if I did copy that, paste that, you know what I mean though. I don't want to deal with this thing ever again. It's some ridiculous thing with so many parameters. I don't want to touch it. I'm gonna leave it like this. I'll just look to see what happens. Also, I thought that guess might actually be close. That guess seemed reasonable to me, so I put it in, and I expected this to maybe converge in 1 or 2. Maybe it goes from 20.9 to like 21, and it converges right there. If I ran this thing, it's going to call that over and over and over, which isn't bad here. But let's hit things like 1,000 times. This isn't easy to calculate. It's got a bunch of logs, and it's got a bunch of exponentials, and it takes more computing power than just solving, than subtracting. Are you good with that? So I can think of 3 ways to define error. Let me know if you can think of more. One of them is you can basically, it's the absolute value of the function when you're solving for the root. So what you're looking for here is if you're solving for the root, you want to find that value of x where this equals 0. That's what you're doing for the root. And not when you have x equals x. That's this for not for iterative. This is if you're just solving for the root. So you have x minus or 0 equals that. We're just looking for the absolute value of that guy. Because when the absolute value of that guy equals 0, or is less than the tolerance, we know that that value of x is pretty close to what we want. Does that make sense to everybody back there? Head nods? Okay. That's one way to do it. Another way to do it is, like I put here, the difference between the next guess and the previous guess. Differences in the guesses. And the third way and also you should probably absolute value all of these. Because you don't want negative tolerances or stuff. Yeah. Because if your error is just negative, let's say this value is actually smaller, let's say the thing goes down, then it's going to end on the first iteration. You don't want that. You want the absolute value of it to be lower. This one's where I said it's how close it is to actually being 0. This one is how close the guesses are to each other. This one is like that cosine x equals x thing, how close that left side is equal to the right side. So if I were to do that on this and implemented number 1, I would take this guy right here, bring this guy over, take that entire thing, absolute value it, and just see how close it is to 0. I just want the absolute value of that guy. Because this minus this should equal 0 when this value converges. Right? So that's what I'm doing here. Second method is what I did here. Third method, like you said before, is I compare the error of at the same time. But this would have to be this guy. Are you seeing this? And they all have advantages and disadvantages at different times. Sometimes you want to use that f of x. Sometimes you want to check the difference between the two. Sometimes you want to check between successive guesses. Does that make sense? You'll get a feel for that as you play around with it. Some people, I don't know which one you like the best. I like this one quite a bit because it gives me a convergence quick. And I feel like I have the physical sense to reason my way through it and go, oh, this is right, or oh, this is not right. Fair enough? Okay. All right. Then I think I'll call for today. I'll have the bisection code ready by next week. And I think we'll go over more root finding methods. We'll go over bisection, regular falsy, Illinois method, Newton-Raphson. And that should take up most of our time. And then our path forward from there. I skipped solving matrices because we missed those 2 weeks, and I was planning on doing it last week. We can go over Gaussian elimination and try diagonal solvers and stuff if you guys want to. Matlab does it for you. This is one of those things where if you have a matrix, you can just do, and that solves a matrix. You don't need to worry about Gaussian elimination. You don't need to worry about LU decomposition, nothing like that. Up to you, though, because LU decomposition is faster. Gaussian is slower. LU decomposition is faster. Try diagonal solvers. There's faster ways to do it than this. Stuff like that. And also, it's just
always only uses Gaussian.
Huh?
MATLAB only uses Gaussian.
MATLAB uses some weird comparative. It's called LAU decomposition. I don't know. It's this weird hybrid. LU sometimes faster for us. Because LU, the advantage is, I don't know if you guys know about what LU decomposition is. It's like you split this matrix up into like an upper and a lower half, and you solve them separately. So basically you can, when you re-enter a new matrix, you don't have to resolve the entire thing. You can just solve the upper half, or you can just solve the lower half. It gives you a little bit of more flexibility kind of when you redo it, but that's kind of the advantage there. Gaussian substitution is the plain old row reduction. You try to get ones all the way down, and then you like back substitution all the way up. That one's pretty standard. It's pretty slow, but that teaches you a lot about loops and about matrix, and I can pull up the code if you want. But I feel like for me, Gaussian was more of a pain in the butt than it was actually worth it.
I don't know, bro. We just think we're not that worried about speed.
Yeah,
We're not computing the Death Star here.
this is true. But I mean, still, it's like
Here's the code for Gaussian. It's like it just turns into these ratios and trying to get little. I mean, it's not that long, but it. I have to teach you the theory behind this just to start with it, which gets a little. I have to teach you matrices, which I'm gonna skim over anyway. But then it just starts to get really weird and funky, and like then you have to worry about a lot of ratios and I don't know. But I think our path forward from here is I could teach you like the Illinois method. Do you see regular falsy? Is it done? Yeah, there it is. And then the secant method. And then the bisection method too, which I'm not sure where it is. I'll ask Steven if he has it. And from there, and we did successive. So then we're gonna go into. I'm gonna try to not delve into chemi stuff. I'm a chemi, so we have a lot of like solving equations that chemis might solve. I'm gonna try to stay away from that, but I'll touch on it just a little bit because it has concepts that are helpful. And then like catalytic discs. Euler's a really good one. I'll teach you guys Euler. But basically we're gonna go from root finding, and then we're gonna start solving differential equations basically, and then I think that'll probably take about 2 more weeks. We have about 6 weeks left. 5 more classes. So 2 more classes for root finding, all that kind of stuff. Start differential equations. That should be about 3 weeks, and then we can finish up with just more advanced stuff. Whatever else advanced stuff we want to do. Boundary conditions, initial value problems, that kind of stuff. Shooting method. But I feel like that should give you a good skill set on how to go from. You should be able to solve most functions or systems of functions or anything like that. You should be able to solve most basic differential equations. Not even basic. You should be able to solve advanced differential equations. And I'm not going to give you a guarantee on the accuracy of those solutions, but use your head. Don't just write down answers. But I feel like at the end of this course, you should be able to go to any of your homeworks from now and not have to do too much of it manually, or at least check it with your laptop. That sound good? Okay.